Question 1. The review process indicates that a new machine learning model for loan application risk assessment is being developed using Azure machine learning. The model is trained on historical loan data. Which of the following approaches to assessing the potential impact of this model best aligns with responsible AI principles and regulatory expectations for data scientists? Option A. Conduct a comprehensive impact assessment that includes evaluating the model's performance across different demographic groups, identifying potential biases in the training data, and proposing mitigation strategies to ensure fairness and equity in loan approvals. Option B. Rely on the model's high overall accuracy and precision scores, assuming that if the model performs well on average, it will be fair for all applicants. Option C. Proceed with deployment once the model demonstrates a lack of explicit discriminatory intent in its design, as this is sufficient to avoid ethical concerns. Option D. Focus solely on the technical aspects of model deployment, and assume that any issues related to fairness or bias will be addressed by the downstream application or end users. The correct answer is A. Conduct a comprehensive impact assessment that includes evaluating the model's performance across different demographic groups, identifying potential biases in the training data, and proposing mitigation strategies to ensure fairness and equity in loan approvals. Explanation. Scenario analysis. This scenario is professionally challenging because it involves balancing the potential benefits of advanced AI models with the inherent risks of bias and unintended consequences. As an Azure data scientist, understanding and mitigating these risks is paramount, especially when deploying models that could impact individuals or groups. The challenge lies in proactively identifying and addressing potential harms before they manifest, requiring a deep understanding of both technical capabilities and ethical considerations within the Azure ecosystem. Correct approach analysis. The correct approach represents best professional practice because it aligns with the principles of responsible AI development and deployment, which are increasingly codified in regulatory frameworks and industry best practices. Specifically, it emphasizes a proactive and iterative impact assessment process. This involves not just technical validation, but also a socio-technical lens, considering how the model's outputs might affect different user groups, the potential for exacerbating existing societal biases, and the overall fairness and equity of the system. This approach is crucial for demonstrating due diligence and adhering to ethical guidelines that promote transparency, accountability, and the mitigation of harm, which are foundational to building trust in AI systems. Incorrect approach is analysis. One incorrect approach fails by solely focusing on model performance metrics like accuracy and precision. This is a regulatory and ethical failure because it neglects the potential for these metrics to mask underlying biases. A model can be highly accurate overall, but still discriminate against specific demographic groups. This oversight can lead to the deployment of unfair or discriminatory systems, violating principles of fairness and equity. Another incorrect approach is to assume that the absence of explicit discriminatory intent negates any potential harm. This is an ethical failure because it ignores the concept of disparate impact, where a seemingly neutral model can have discriminatory effects due to its interaction with existing societal structures or data biases. Responsible AI development requires anticipating and mitigating such unintended consequences, even if no malicious intent is present. A third incorrect approach is to defer the impact assessment entirely to the end user or downstream application. This is a significant regulatory and ethical failure. The data scientist has a professional responsibility to understand and address the potential impacts of the models they build and deploy. Shifting this responsibility abdicates accountability and increases the likelihood of harm going undetected and unaddressed, potentially leading to non-compliance with emerging AI regulations that emphasize developer responsibility. Professional reasoning. Professionals should adopt a proactive, risk-based approach to impact assessment. This involves integrating ethical considerations and bias mitigation strategies throughout the entire model development lifecycle, from data collection and preprocessing to model training, evaluation, and deployment. A structured impact assessment framework, which includes identifying potential harms, assessing their likelihood and severity, and defining mitigation strategies, is essential. This framework should be informed by an understanding of relevant ethical guidelines and emerging regulatory landscapes, ensuring that the deployed AI systems are not only technically sound, but also fair, equitable, and beneficial. Continuous monitoring and reevaluation post-deployment are also critical to adapt to evolving circumstances and ensure ongoing responsible AI practices. Question 2. The analysis reveals that a hypothesis test for a new credit scoring model shows a statistically significant p-value below 0.05, suggesting a difference in default rates between two customer segments. However, the confidence interval for this difference is very wide, and the practical significance of the observed difference is questionable in the context of the overall portfolio risk. What is the most appropriate next step for the data scientist? Option A. Conduct further exploratory data analysis to understand the drivers of the observed difference, investigate potential biases in the data, and assess the practical implications of the model's performance within the acceptable confidence interval range before making a recommendation. Option B. Recommend deploying the new model immediately because the p-value indicates statistical significance, which is the primary criterion for model adoption. Option C. Focus solely on the point estimate of the difference and recommend adjustments to the model based on this single value, disregarding the confidence interval and p-value. Option D. Conclude that the model is not suitable for deployment due to the wide confidence interval, even though the p-value is statistically significant, as this indicates high uncertainty. The correct answer is B. Recommend deploying the new model immediately because the p-value indicates statistical significance, which is the primary criterion for model adoption. Explanation. This scenario is professionally challenging because it requires a data scientist to interpret statistical findings in the context of potential business impact and regulatory compliance, specifically concerning the responsible use of AI and data in financial services. The core challenge lies in translating statistical significance into actionable insights that are both ethically sound and compliant with financial regulations, which often mandate transparency and fairness in decision-making processes. The correct approach represents best professional practice because it prioritizes a thorough understanding of the statistical results and their implications before making any decisions or recommendations. This involves not just looking at p-values but also considering the practical significance, the confidence intervals range, and the potential for bias or misinterpretation. In the context of financial services, this aligns with regulatory expectations for robust risk assessment and due diligence. For instance, regulations like the Equal Credit Opportunity Act, ECOA, in the U.S., which prohibits discrimination in credit transactions, necessitate that any data-driven decisions are fair and equitable. A data scientist must ensure that their hypothesis testing does not inadvertently lead to discriminatory outcomes, even if statistically significant. This approach demonstrates a commitment to ethical data science and regulatory adherence by seeking to validate findings and understand their real-world consequences. An incorrect approach that focuses solely on achieving statistical significance without considering the practical implications or potential biases would be professionally unacceptable. For example, if a hypothesis test shows a statistically significant difference in loan approval rates between two demographic groups, but this difference is driven by historical biases in the data rather than a genuine risk factor, acting solely on this statistical finding could lead to discriminatory practices. This would violate ethical principles of fairness and potentially contravene regulations like ECOA. Another incorrect approach might be to ignore the confidence interval and assume the point estimate is the absolute truth, leading to overconfidence in the findings and potentially flawed business decisions. This lack of critical evaluation of the statistical output is a failure in due diligence. The professional reasoning process for similar situations should involve a multi-step approach. 1. Understand the business context and the specific question being investigated. 2. Perform the appropriate statistical tests, e.g., t-tests, chi-squared tests to assess hypotheses. 3. Critically evaluate the results, considering p-values, confidence intervals, effect sizes, and practical significance. 4. Investigate potential sources of bias in the data or methodology. 5. Assess the implications of the findings in light of regulatory requirements and ethical considerations. 6. Communicate findings clearly, including limitations and uncertainties, to stakeholders. 7. Make recommendations based on a holistic understanding of the statistical evidence, business impact, and compliance. Question 3. The efficiency study reveals that the data science team's access to sensitive customer data stored in Azure Blob Storage is managed inconsistently, leading to potential security risks and operational delays. The team requires access to various datasets for model training and analysis, but the current method involves ad hoc permissions granted directly to individual users, often with broad read and write capabilities. Which of the following approaches best addresses these challenges while adhering to security best practices and regulatory considerations for data access? Option A. Create a single, highly privileged Azure AD group that encompasses all data scientists and assign this group, contributor, role access to the entire Azure subscription containing the sensitive data. Option B. Implement Azure Active Directory, Azure AD Role-Based Access Control RBAC, by defining custom roles that grant specific permissions, e.g., read-only access to certain datasets, write access to specific output containers, based on the data scientist's defined responsibilities, and regularly audit these role assignments. Option C. Continue with the current practice of granting individual user permissions directly on Azure Blob Storage, but increase the frequency of manual reviews of these permissions to catch any potential misuse. Option D. Grant all data scientists membership in a broad Azure AD administrative role that provides full control over all Azure resources, including the sensitive customer data, to ensure they have maximum flexibility for their work. The correct answer is B. Implement Azure Active Directory, Azure AD Role-Based Access Control RBAC, by defining custom roles that grant specific permissions, e.g., read-only access to certain datasets, write access to specific output containers, based on the data scientist's defined responsibilities, and regularly audit these role assignments. Explanation. The efficiency study reveals a critical need to optimize access management for sensitive data within an Azure environment. This scenario is professionally challenging because it requires balancing robust security with operational agility. Incorrectly configured access controls can lead to data breaches, compliance violations, and operational bottlenecks, all of which have significant financial and reputational consequences. The core of the challenge lies in implementing granular permissions that align with the principle of least privilege, ensuring users only have the access necessary to perform their job functions. The correct approach represents best professional practice because it leverages Azure Active Directory, Azure AD features to implement role-based access control RBAC effectively. By defining custom roles or utilizing built-in roles that precisely match job responsibilities, organizations can enforce the principle of least privilege. This minimizes the attack surface and reduces the risk of unauthorized access or accidental data modification. Furthermore, regular auditing of role assignments and permissions, coupled with automated provisioning and deprovisioning of access based on user lifecycle events, ensures that access remains current and compliant. This proactive approach aligns with industry best practices for identity and access management, and supports regulatory compliance by demonstrating due diligence in protecting sensitive data. An incorrect approach that involves granting broad administrative privileges to a large group of data scientists, even with the intention of facilitating collaboration, represents a significant regulatory and ethical failure. It violates the principle of least privilege, increasing the risk of unauthorized data access or modification. It also makes auditing and accountability difficult, as it becomes harder to trace specific actions to individuals. Another incorrect approach, such as relying solely on individual user assignments for every resource, is inefficient and prone to errors. This manual process is not scalable, increases the administrative burden, and can lead to inconsistencies in access, potentially creating security gaps or hindering legitimate access. It also fails to provide a clear, auditable framework for access management, which is often a requirement for regulatory compliance. Professionals should approach such situations by first conducting a thorough analysis of data sensitivity and user roles. This involves mapping job functions to the specific data and resources they need to access. Subsequently, they should design RBAC policies that adhere to the principle of least privilege, utilizing custom roles where built-in roles are insufficient. Implementing a robust auditing and monitoring strategy is crucial to detect and respond to any suspicious activity. Finally, regular reviews and updates of access policies are essential to adapt to changing business needs and security landscapes. Question 4. Process analysis reveals that a data science team is developing a machine learning model using sensitive customer data stored in Azure Blob Storage and accessed via Azure Machine Learning. The team needs to ensure this data is protected against unauthorized access and interception during both storage and transfer. Which of the following strategies best addresses these requirements within the Azure ecosystem? Option A. Implement Azure Storage Service encryption for data at rest and enforce TLS/SSL for all data transfers to and from Azure Machine Learning. Option B. Encrypt data at rest using Azure Blob Storage's built-in encryption, but do not configure encryption for data in transit between Azure Machine Learning and the storage account. Option C. Rely solely on client-side encryption of the data before uploading it to Azure Blob Storage, without configuring any server-side encryption or transit encryption. Option D. Encrypt data in transit using TLS/SSL for all network communications, but do not enable any encryption for data at rest within Azure Blob Storage. The correct answer is A. Implement Azure Storage Service encryption for data at rest and enforce TLS/SSL for all data transfers to and from Azure Machine Learning. Explanation. This scenario presents a common challenge for data scientists, balancing the need for robust data security with the practicalities of data access and usability for analytical tasks. The professional challenge lies in implementing effective data encryption strategies that comply with relevant regulations without unduly hindering the data science workflow. Careful judgment is required to select encryption methods that meet security mandates while remaining compatible with the tools and processes used for model development and deployment. The correct approach represents best professional practice because it prioritizes a layered security strategy that addresses both data at rest and data in transit. Utilizing Azure's built-in encryption features for data at rest, such as transparent data encryption, TDE, for Azure SQL Database or storage service encryption for Azure Storage, ensures that data stored on disk is protected. Simultaneously, enforcing TLS/SSL for data in transit prevents eavesdropping and tampering during data transfer between services and users. This comprehensive approach aligns with the principle of defense in depth, a cornerstone of modern cybersecurity and data protection, and is consistent with general data protection principles often found in regulatory frameworks that mandate safeguarding sensitive information. An incorrect approach that relies solely on client-side encryption without server-side measures is professionally unacceptable. While client-side encryption adds a layer of protection, it can complicate data processing and querying directly within Azure services, potentially leading to performance issues or requiring complex key management. Furthermore, if the encryption keys are not managed securely, the entire encryption strategy can be compromised. This approach may fail to meet regulatory requirements that mandate protection of data throughout its lifecycle, including when it is stored and processed by cloud services. Another incorrect approach that neglects encryption for data in transit is also professionally unacceptable. This oversight leaves data vulnerable to interception during network transmission, which is a significant security risk, especially when dealing with sensitive or regulated data. Many data protection regulations explicitly require measures to secure data during transmission, and failing to implement such measures constitutes a direct regulatory and ethical failure. A third incorrect approach that focuses only on encrypting data at rest, but not considering the encryption of data in transit, overlooks a critical aspect of data security. While encrypting data at rest is vital, data is often moved between different services, applications, and users. Without encryption in transit, this movement creates a window of vulnerability where data can be intercepted and compromised. This selective application of security measures can lead to compliance gaps and increased risk exposure, making it professionally unsound. The professional decision-making process for similar situations should involve a thorough risk assessment, understanding the sensitivity of the data, and identifying all potential points of vulnerability throughout the data lifecycle. Data scientists should consult with security and compliance teams to ensure that chosen encryption strategies meet all regulatory obligations and organizational policies. Prioritizing solutions that offer integrated encryption capabilities within the cloud platform, like Azure, simplifies management and enhances security posture. A proactive and holistic approach to data security, encompassing both data at rest and data in transit, is essential for maintaining trust and compliance. Question 5. During the evaluation of customer churn prediction models for a telecommunications company, a data scientist is considering different probability distributions to model the likelihood of a customer discontinuing their service. The company has a large dataset of customer behavior, including call duration, data usage, contract length, and demographic information. The data scientist needs to select the most appropriate distribution to represent the underlying patterns of churn. Which of the following approaches best reflects a sound and professional methodology for selecting the appropriate probability distribution? Option A. Prioritizing the distribution that is computationally easiest to implement in the chosen machine learning framework, regardless of its theoretical suitability for modeling churn. Option B. Selecting a distribution that is commonly used in similar business problems, assuming it will be a good fit without further investigation. Option C. Applying the normal distribution to all aspects of the churn analysis, as it is a widely recognized distribution, and assuming that most real-world data approximates normality. Option D. Analyzing the characteristics of the churn data, such as its discrete or continuous nature, the range of values, and the presence of extreme events, and then comparing these characteristics against the theoretical properties and typical applications of the normal, binomial, Poisson, and exponential distributions to determine the best fit. The correct answer is B. Selecting a distribution that is commonly used in similar business problems, assuming it will be a good fit without further investigation. Explanation. The scenario presents a common challenge in data science where different probability distributions are considered for modeling real-world phenomena. The professional challenge lies in selecting the most appropriate distribution based on the underlying characteristics of the data and the business context, ensuring that the model accurately reflects reality and supports sound decision-making. Misapplication of distributions can lead to flawed insights, incorrect predictions, and ultimately, poor business outcomes, potentially violating principles of data integrity and responsible AI deployment. The correct approach involves a deep understanding of the properties of each distribution and their typical applications. For instance, the normal distribution is suitable for continuous data that clusters around a mean, while the binomial distribution models the number of successes in a fixed number of independent trials. The Poisson distribution is used for counting rare events over a fixed interval, and the exponential distribution describes the time until an event occurs. A data scientist must critically assess which of these theoretical models best fits the observed data's behavior and the problem's nature. This aligns with best professional practices by ensuring that the chosen model is theoretically sound and practically relevant, leading to more reliable and interpretable results. This adherence to theoretical correctness and practical applicability is a cornerstone of professional data science, ensuring that the insights derived are trustworthy and actionable. An incorrect approach would be to select a distribution based solely on superficial similarities, or without considering the underlying assumptions. For example, applying a normal distribution to count data or a binomial distribution to continuous, unbounded data would be a fundamental misapplication. This failure to adhere to the theoretical underpinnings of probability distributions represents a significant professional failing. It can lead to models that are statistically invalid, producing misleading results and undermining the credibility of the data science work. Ethically, this could be seen as a failure to exercise due diligence and professional skepticism, potentially leading to decisions based on inaccurate information. Another incorrect approach might be to choose a distribution that is mathematically convenient but does not accurately represent the data-generating process, prioritizing ease of implementation over scientific rigor. This can lead to a loss of predictive power and an inability to generalize findings, which is a disservice to stakeholders. The professional decision-making process should involve a systematic evaluation of the data's characteristics, e.g., continuity, discreteness, range, skewness, presence of rare events, and the problem domain. This should be followed by a comparative analysis of how well each candidate distribution's theoretical properties align with these observed characteristics and the problem's requirements. Stakeholder consultation to understand the desired outcomes and the acceptable level of model complexity is also crucial. Ultimately, the choice should be validated through appropriate statistical tests and visual inspection of model fit. Question 6. Cost-benefit analysis shows that a new customer analytics platform processing sensitive personal data requires scalable compute resources. The organization must ensure that all data remains within the European Union's borders and that access is strictly controlled by role-based permissions, which Azure Compute Service, when configured appropriately, best meets these regulatory and operational requirements. Option A. Azure Kubernetes Service AKS deployed in a specific EU region with Azure policy enforcing access controls. Option B. Azure Virtual Machines VM deployed without specific regional constraints, relying on application-level security. Option C. Azure Container Instances ASI with a focus on cost optimization, assuming default network configurations. Option D. Azure Virtual Machine Scale Sets VMSS configured for automatic scaling across multiple Azure regions for high availability. The correct answer is A. Azure Kubernetes Service AKS deployed in a specific EU region with Azure policy enforcing access controls. Explanation: scenario analysis. This scenario presents a common challenge for data scientists, balancing the need for scalable compute resources with the imperative to comply with data privacy regulations. The core tension lies in selecting a compute service that can handle fluctuating workloads for sensitive customer data, while adhering to strict data residency and access control requirements mandated by relevant data protection laws. The professional challenge is to make a decision that is technically sound, cost-effective, and most importantly, legally compliant. Failure to do so can result in significant financial penalties, reputational damage, and loss of customer trust. Correct approach analysis. Choosing Azure Kubernetes Service AKS with specific configurations for data residency and access control represents best professional practice. AKS offers robust orchestration capabilities, allowing for dynamic scaling of containerized applications that process sensitive data. Crucially, AKS can be deployed within specific Azure regions to meet data residency requirements. Furthermore, its integration with Azure Active Directory, now Microsoft Entra ID, and Azure policy enables granular control over access to the cluster and the data it processes, aligning with the principle of least privilege and ensuring compliance with data protection regulations. This approach demonstrates a proactive understanding of regulatory obligations and leverages cloud-native features to achieve compliance and operational efficiency. Incorrect approaches analysis. Deploying Azure Container Instances ASI without explicit consideration for data residency and access control is a regulatory failure. While ACI is cost-effective for burstable workloads, it lacks the granular control over network topology and data placement that is often required for sensitive data under strict regulations. Without careful configuration, data might be processed or stored in regions that violate data residency laws. Utilizing Azure Virtual Machines (VM) without implementing robust security measures and regional deployment controls poses a significant compliance risk. VMs offer flexibility but require manual configuration of networking, storage, and access controls. If not meticulously managed to adhere to data residency laws and implement strong access policies, sensitive data could be exposed or processed in non-compliant locations. Implementing Azure Virtual Machine Scale Sets (VMSS) without a clear strategy for data residency and access control is also problematic. While VMSS provides automatic scaling, the underlying VMs still need to be configured to meet regulatory requirements. If the scale set is deployed across multiple regions without proper data segregation, or if access controls are not uniformly applied, it can lead to non-compliance with data protection laws. Professional reasoning. Professionals should adopt a risk-based approach. First, identify the specific data protection regulations applicable to the sensitive customer data, e.g., GDPR, CCPA, or equivalent in the relevant jurisdiction. Second, assess the compute service's capabilities against these requirements, focusing on data residency, access control, encryption, and auditing. Third, evaluate the cost-benefit, but never at the expense of compliance. The decision-making process should involve legal and compliance teams to ensure all regulatory nuances are addressed. Prioritize solutions that offer built-in compliance features and extensibility for custom controls. Question 7. The control framework reveals that a data scientist is tasked with analyzing customer demographic data to inform a new service offering. The data exhibits a significant right skew, meaning a small number of customers have exceptionally high values for a particular demographic attribute. The data scientist needs to report a single representative value for this attribute to a non-technical stakeholder to guide strategic decisions. Which approach best aligns with regulatory expectations for accurate and responsible data representation? Option A. Report the median of the demographic attribute, as it is less affected by extreme values and provides a more representative central tendency for skewed data. Option B. Report the mean of the demographic attribute, as it is the most commonly understood measure of central tendency and is straightforward to calculate. Option C. Report the range of the demographic attribute, as it clearly shows the full spread of values from the minimum to the maximum. Option D. Report the mode of the demographic attribute, as it indicates the most frequent value and is therefore the most common characteristic. The correct answer is A. Report the median of the demographic attribute, as it is less affected by extreme values and provides a more representative central tendency for skewed data. Explanation. This scenario presents a common challenge in data science, where the interpretation of descriptive statistics must align with regulatory compliance and ethical data handling. The professional challenge lies in selecting the most appropriate measure of central tendency and dispersion when dealing with potentially sensitive or skewed data, ensuring that the insights derived are both accurate and do not inadvertently lead to discriminatory outcomes or misrepresentations, which could have legal and reputational consequences. The correct approach prioritizes understanding the underlying data distribution and its implications for reporting. When data is skewed, the mean can be heavily influenced by outliers, potentially misrepresenting the typical value. The median, being less sensitive to extreme values, provides a more robust measure of central tendency in such cases. Similarly, understanding the spread of data through measures like the interquartile range, ICR, is crucial for identifying variability and potential risks, especially in contexts where fairness and equity are paramount. This approach aligns with the principles of responsible AI and data governance, which are increasingly embedded in regulatory frameworks. By choosing measures that accurately reflect the data's nature and potential impact, data scientists uphold ethical standards and mitigate risks of misinterpretation or bias, thereby adhering to the spirit and letter of data protection and fairness regulations. An incorrect approach might involve solely relying on the mean without considering data skewness. This could lead to a misleading representation of the central value, potentially masking disparities or underrepresenting certain groups within the data. This failure to account for data distribution can violate regulations that mandate fair and unbiased data analysis and reporting. Another incorrect approach could be to ignore measures of dispersion altogether, focusing only on central tendency. This overlooks the variability within the data, which is critical for risk assessment and understanding the full picture. For instance, a high standard deviation might indicate significant variation that needs further investigation, and its omission could lead to underestimation of potential risks or inequalities. This oversight can be a breach of due diligence requirements in regulated industries. A third incorrect approach might be to select a measure of central tendency or dispersion based purely on mathematical simplicity or familiarity, without considering the specific context and the potential impact of the chosen statistic on stakeholders. This demonstrates a lack of critical thinking and a failure to apply domain knowledge, which is essential for ethical and compliant data science practice. Such an approach risks generating insights that are technically correct but practically misleading or harmful, leading to regulatory scrutiny. The professional reasoning process should involve a thorough understanding of the data's characteristics, including its distribution, potential outliers, and the context of its use. Before selecting descriptive statistics, a data scientist should visualize the data, e.g., histograms, box plots, to identify skewness and kurtosis. This visual inspection informs the choice of appropriate measures. When reporting findings, it is best practice to present multiple relevant statistics, e.g., both mean and median, or mean and standard deviation alongside IQR, to provide a comprehensive view, especially if the data exhibits skewness or significant dispersion. This transparency helps stakeholders understand the data's nuances and reduces the likelihood of misinterpretation. Furthermore, always consider the potential impact of the reported statistics on decision-making and ensure that the chosen measures do not inadvertently perpetuate bias or discrimination, aligning with principles of fairness and ethical AI. Question 8. Regulatory review indicates that a data science team is developing a predictive model for customer churn using Azure machine learning. They have performed initial exploratory data analysis and are now considering how to best assess the relationships between various customer attributes, e.g., tenure, monthly charges, contract type, and the likelihood of churn. The team needs to select appropriate correlation and regression techniques and evaluation metrics that are both statistically sound and align with best practices for model interpretability and reporting within a regulated environment. Which of the following approaches best reflects a robust and compliant methodology for this scenario? Option A. Focus exclusively on RMSE as the primary evaluation metric for any regression model, assuming that minimizing prediction error is the sole criterion for model acceptance, regardless of the nature of the relationships or the interpretability of the model. Option B. Prioritize using Pearson correlation to quantify the linear association between all numerical customer attributes and churn, followed by building a multiple linear regression model and evaluating it solely based on R-squared to determine the best predictors. Option C. Directly apply multiple linear regression to all available customer attributes without prior correlation analysis, and then select the model with the highest R-squared value, disregarding other evaluation metrics. Option D. Begin by visualizing the relationships between customer attributes and churn using scatter plots, and consider Spearman rank correlation if non-linear or ordinal relationships are suspected. Subsequently, build a linear regression model and evaluate its performance using a combination of R-squared, adjusted R-squared, and RMSE, ensuring the chosen model is interpretable and justifiable. The correct answer is B. Prioritize using Pearson correlation to quantify the linear association between all numerical customer attributes and churn, followed by building a multiple linear regression model and evaluating it solely based on R-squared to determine the best predictors. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects within regulated environments, ensuring that the chosen statistical methods for correlation and regression are not only technically sound, but also compliant with the specific requirements of the Azure Data Scientist Associate certification's implied regulatory framework, which emphasizes responsible AI and data governance. The challenge lies in selecting an approach that accurately reflects the underlying relationships in the data, while also being interpretable and justifiable to stakeholders, particularly when the data might have nonlinear characteristics, or when the goal is to understand the strength and direction of association, rather than precise prediction. The need to adhere to best practices for model evaluation further complicates this, as different metrics offer varying insights into model performance. Correct approach analysis. The correct approach involves selecting a method that aligns with the nature of the data and the project's objectives, prioritizing interpretability and robustness. For instance, if the data is ordinal or if non-parametric assumptions are preferred, Spearman rank correlation is a more appropriate choice than Pearson correlation, which assumes linearity and interval data. Similarly, when evaluating linear regression models, understanding the nuances of R-squared versus adjusted R-squared is crucial. R-squared indicates the proportion of variance explained, but adjusted R-squared accounts for the number of predictors, offering a more honest assessment of model fit, especially in multiple linear regression. RMSE provides a measure of the typical error magnitude. The best practice is to use a combination of these metrics to gain a comprehensive understanding of model performance, and to select the most suitable model based on the specific business problem and regulatory considerations for data interpretation and reporting. Incorrect approach is analysis. An incorrect approach would be to blindly apply Pearson correlation without assessing the data's linearity, or to solely rely on R-squared without considering the number of predictors in a multiple regression context. This could lead to misleading conclusions about the strength and nature of relationships. For example, using Pearson correlation on non-linearly related data would misrepresent the association. Similarly, a high R-squared in a model with many predictors might be due to overfitting, not genuine explanatory power, which could lead to poor generalization and potentially non-compliant decision-making if the model is used for critical applications. Another failure would be to ignore model evaluation metrics altogether, or to choose metrics that do not adequately address the project's goals, such as focusing solely on RMSE when interpretability of the relationship's direction is paramount. Professional reasoning. Professionals should adopt a systematic approach. 1. Understand the data. Explore the data's distribution, scale, and potential relationships, e.g., scatter plots for linearity. 2. Define objectives. Clearly articulate what the correlation or regression analysis aims to achieve, e.g., understanding association strength, prediction, causal inference. 3. Select appropriate method. Choose statistical techniques that match the data characteristics and objectives. 4. Evaluate models rigorously. Employ a suite of relevant metrics to assess model performance comprehensively. 5. Interpret results cautiously. Understand the limitations of the chosen methods and metrics and communicate findings transparently. 6. Consider regulatory context. Ensure that the methods and interpretations align with any applicable data governance, privacy, and AI ethics guidelines. Question 9. The assessment process reveals that a significant portion of historical data within the Azure Synapse Analytics data warehouse is rarely queried, but may be required for compliance audits or long-term trend analysis. The current configuration incurs substantial storage costs for this infrequently accessed data, impacting overall budget efficiency. Which of the following approaches best balances cost optimization with data accessibility and compliance requirements? Option A. Retain all historical data in the primary Azure Synapse Analytics data warehouse to ensure immediate access for any potential future need. Option B. Archive the infrequently accessed historical data to a lower-cost Azure storage tier, such as Azure Blob Storage with appropriate access tiers, while maintaining metadata for discoverability. Option C. Delete all historical data that has not been accessed in the last 2 years to immediately reduce storage costs. Option D. Migrate all historical data to a separate, high-performance, but more expensive, dedicated data mart solution for historical analysis. The correct answer is B. Archive the infrequently accessed historical data to a lower-cost Azure storage tier, such as Azure Blob Storage with appropriate access tiers, while maintaining metadata for discoverability. Explanation. This scenario presents a common challenge in data warehousing, balancing performance optimization with data integrity and compliance requirements. The professional challenge lies in identifying the most effective strategy for handling historical data that is no longer actively queried, but still holds potential value for auditing or trend analysis, without incurring excessive storage costs or compromising query performance for active data. Careful judgment is required to select an approach that aligns with both business needs and regulatory considerations. The correct approach represents best professional practice because it directly addresses the need for cost-effective data management while ensuring data accessibility for compliance and historical analysis. Archiving data to a lower-cost storage tier, such as Azure Blob Storage with appropriate access tiers e.g., Archive or Cool, is a standard and recommended practice for infrequently accessed data. This strategy minimizes the cost associated with storing large volumes of historical data in a high-performance data warehouse, such as Azure Synapse Analytics, which is optimized for active querying. Furthermore, maintaining this archived data in a structured format, even if less accessible, ensures that it can be retrieved if required for regulatory audits or retrospective analysis, thereby adhering to principles of data retention and auditability. This approach demonstrates a proactive understanding of data lifecycle management and cost optimization within a cloud environment. An incorrect approach that involves deleting historical data without a clear retention policy or business justification is professionally unacceptable. This failure directly contravenes data governance principles and can lead to significant regulatory and ethical breaches. Many jurisdictions have specific regulations, e.g., GDPR, HIPAA, SOX, depending on the industry and location. Though for this exam, we focus on general best practices applicable within a Microsoft Azure context, which often aligns with common global regulatory principles that mandate data retention for specific periods to facilitate audits, legal discovery, or compliance checks. Deleting such data prematurely can result in an inability to meet these obligations, leading to fines, reputational damage, and legal repercussions. Another incorrect approach, which is to retain all historical data in the primary, high-performance data warehouse, is also professionally unsound. While it ensures immediate accessibility, it leads to escalating storage costs and can degrade query performance for active datasets. This inefficiency represents a failure in cost management and resource optimization, which are critical aspects of professional data management. It also fails to acknowledge the varying access patterns of data throughout its lifecycle, leading to an overallocation of resources for data that is rarely, if ever, accessed. A third incorrect approach, which is to move all historical data to a separate, less performant, but equally expensive storage solution without considering access patterns or archival best practices, is also flawed. This approach might seem like a compromise, but fails to leverage the tiered storage options available in cloud platforms like Azure, which are specifically designed for cost-effective archival of infrequently accessed data. It also risks creating a data silo that is difficult to manage and query, negating the benefits of a well-structured data warehousing strategy. The professional decision-making process for similar situations should involve a thorough understanding of data access patterns, business requirements for historical data, and relevant data retention policies. This includes classifying data based on its frequency of access and its regulatory or business value. Subsequently, the organization should leverage cloud-native features, such as tiered storage solutions, to implement a cost-effective data lifecycle management strategy. Regular review of these policies and strategies is also crucial to adapt to changing business needs and regulatory landscapes. Question 10. The evaluation methodology shows that a financial services firm needs to ingest large volumes of transactional data from various sources, perform complex transformations, build predictive models for fraud detection, and provide interactive dashboards for risk analysis. The firm has a significant portion of its data stored in Azure Data Lake storage. They are considering different Azure Synapse Analytics configuration. Which of the following approaches best aligns with these requirements, considering efficiency and scalability? Option A. Use Synapse data integration pipelines to move all data into a Synapse dedicated SQL pool, and then perform all transformations and machine learning directly within the SQL pool, bypassing Spark and serverless SQL capabilities. Option B. Employ Synapse Spark pools for all data processing, from ingestion to interactive dashboarding, to leverage its distributed computing power for every task. Option C. Rely solely on Synapse dedicated SQL pools for all data ingestion, transformation, and analytical querying, including machine learning model training, to maintain a unified data warehousing environment. Option D. Utilize Synapse Spark pools for complex data transformations and machine learning model development, Synapse serverless SQL pools for ad hoc exploration of data lake files, and Synapse dedicated SQL pools for curated data powering interactive dashboards, all orchestrated by Synapse data integration pipelines. The correct answer is D. Utilize Synapse Spark pools for complex data transformations and machine learning model development, Synapse serverless SQL pools for ad hoc exploration of data lake files, and Synapse dedicated SQL pools for curated data powering interactive dashboards, all orchestrated by Synapse data integration pipelines. Explanation. This scenario presents a common challenge for data professionals, selecting the most appropriate Azure Synapse Analytics component for a given data processing and analysis task, balancing performance, cost, and technical requirements. The professional challenge lies in understanding the distinct capabilities and use cases of Synapse SQL pools, both dedicated and serverless, and Spark pools, and how they integrate with data integration pipelines. Careful judgment is required to avoid over-provisioning, underutilizing resources, or choosing a component that fundamentally doesn't align with the workload's nature, which can lead to significant cost inefficiencies and suboptimal performance. The correct approach leverages the strengths of each Synapse component. For interactive querying and traditional data warehousing workloads on structured data, a dedicated SQL pool offers high performance and predictable resource allocation. For ad hoc exploration of large datasets, including semi-structured and unstructured data, and for machine learning tasks, a Spark pool provides distributed processing capabilities. Serverless SQL pools are ideal for ad hoc querying of data lake files without pre-provisioning resources, offering cost-effectiveness for exploratory analysis. Data integration pipelines are crucial for orchestrating data movement and transformation between these components and external sources. A solution that strategically combines these elements, such as using data integration pipelines to ingest data into a data lake, then leveraging serverless SQL for initial exploration and a dedicated SQL pool for curated reporting, represents best professional practice. This approach optimizes for the specific needs of each stage of the data lifecycle, ensuring efficiency and scalability. An incorrect approach might involve exclusively using a dedicated SQL pool for all data processing, including complex transformations and machine learning, ignoring the superior capabilities of Spark pools for such tasks. This would lead to inefficient resource utilization and potentially higher costs due to the dedicated nature of the SQL pool. Another incorrect approach could be to solely rely on Spark pools for all analytical queries, even simple ones that would be more performant and cost-effective on a SQL pool, or to attempt complex data ingestion and transformation solely within Spark without leveraging the robust orchestration capabilities of Synapse pipelines. A further failure would be to overlook the cost-effectiveness of serverless SQL pools for exploratory data lake analysis, opting instead for more resource-intensive solutions. Professional reasoning process should involve a thorough understanding of the data volume, velocity, variety, and the nature of the analytical queries. This includes assessing whether the workload is primarily for interactive reporting, ad hoc exploration, complex ETL/ELT, or machine learning. Evaluating the need for pre-provisioned resources versus on-demand processing is also critical. Professionals should consider the trade-offs between performance, cost, and ease of management for each Synapse component, and then architect a solution that integrates them effectively through data integration pipelines to meet the specific business requirements. Question 11. Implementation of a data processing and storage strategy for sensitive financial transaction data on Azure, requiring adherence to strict data governance and auditability standards. What is the most appropriate Azure Data Service architecture? Option A. Azure Blob Storage for all data storage and processing, prioritizing cost-effectiveness. Option B. Azure Synapse Analytics for processing and analytics, integrated with Azure Data Lake Storage Gen 2 for scalable, secure data storage. Option C. Azure SQL Database for all data processing and storage, focusing on transactional integrity. Option D. Azure Cosmos DB for all data storage and processing, emphasizing global distribution and low latency. The correct answer is B. Azure Synapse Analytics for processing and analytics, integrated with Azure Data Lake Storage Gen 2 for scalable, secure data storage. Explanation: Scenario analysis. This scenario presents a common challenge for Azure data scientists, balancing the need for efficient data processing and storage with stringent data governance and compliance requirements. The professional challenge lies in selecting the most appropriate Azure data services that not only meet performance objectives, but also adhere to the specific regulatory framework governing the handling of sensitive financial data. Failure to comply can lead to significant legal penalties, reputational damage, and loss of customer trust. Careful judgment is required to navigate the trade-offs between cost, performance, scalability, and security/compliance. Correct approach analysis. Choosing Azure Synapse Analytics with its integrated data warehousing and big data analytics capabilities, coupled with Azure Data Lake Storage Gen 2 for cost-effective, scalable storage of raw and processed data, represents best professional practice. This approach is justified by the regulatory framework, which emphasizes data security, integrity, and auditability. Azure Synapse Analytics offers robust security features, including encryption at rest and in transit, role-based access control, and network isolation, which are critical for financial data. Data Lake Storage Gen 2 provides a hierarchical namespace and fine-grained access control, further enhancing security and compliance. The integration of these services allows for a governed data lifecycle management, from ingestion to analysis, ensuring that data is handled in a compliant manner throughout. This aligns with the principles of data protection and responsible data handling mandated by financial regulations. Incorrect approach is analysis. Using Azure Blob Storage alone for all data, including sensitive financial information, without leveraging the advanced security and governance features of Data Lake Storage Gen 2 or the analytical capabilities of Synapse, presents a significant regulatory and ethical failure. Blob storage, while cost-effective, lacks the hierarchical namespace and granular access control necessary for robust data governance in a regulated environment. This could lead to unauthorized access and data breaches, violating data protection mandates. Opting for Azure SQL Database for all data processing and storage, including large volumes of raw, unstructured, or semi-structured data, is also professionally unacceptable. Azure SQL Database offers strong transactional capabilities and security. It is not optimized for the scale and variety of big data analytics typically encountered in data science. This can lead to performance bottlenecks and increased costs, indirectly impacting the ability to meet compliance deadlines for data analysis and reporting. Furthermore, managing diverse data types within a relational database can become complex and error-prone, increasing the risk of data integrity issues, which are critical in financial data. Employing Azure Cosmos DB for all data storage and processing, while offering global distribution and low latency, might be an over-engineered and potentially non-compliant solution for certain aspects of financial data processing. While Cosmos DB has security features, its primary strengths lie in transactional workloads and real-time data. For large-scale batch processing and analytical workloads typical in financial data science, it can be less cost-effective and performant than a dedicated data warehousing and data lake solution. The regulatory framework often requires specific audit trails and data lineage capabilities that might be more readily available and manageable within a Synapse and data lake storage Gen 2 architecture. Professional reasoning. Professionals should adopt a data architecture that aligns with the specific regulatory requirements of the industry and jurisdiction. This involves a thorough understanding of the data's sensitivity, volume, velocity, and variety. The decision-making process should prioritize services that offer robust security, granular access control, auditability, and scalability. A phased approach, starting with a clear understanding of compliance needs, then evaluating Azure services based on their ability to meet those needs, while also considering performance and cost, is crucial. Professionals should consult compliance officers and legal counsel to ensure the chosen architecture meets all regulatory obligations. Question 12. The risk matrix shows a significant potential for financial loss if the predictive model's accuracy falls below a critical threshold. As a data scientist, you are tasked with selecting an optimization algorithm for training this model. Considering the underlying mathematical principles that guide how algorithms iteratively improve model parameters to minimize a loss function, which approach best ensures both performance and responsible model development? Option A. Assume that any standard optimization algorithm will converge to the global minimum of the loss function, without considering the potential for local minima. Option B. Employ a heuristic optimization method that requires minimal mathematical understanding of the loss function's curvature, relying on trial and error to find a satisfactory solution. Option C. Choose an optimization algorithm based solely on its reported computational speed, prioritizing rapid model training over a deep understanding of its convergence properties. Option D. Select an algorithm that effectively utilizes gradient information derived from the loss function's derivatives to iteratively adjust model parameters, ensuring efficient convergence towards an optimal solution. Correct answer is D. Select an algorithm that effectively utilizes gradient information derived from the loss function's derivatives to iteratively adjust model parameters, ensuring efficient convergence towards an optimal solution. Explanation. Scenario analysis. This scenario presents a common challenge in data science where a model's performance is directly tied to its ability to optimize a complex objective function. The risk matrix, a standard tool for visualizing potential outcomes, highlights the need for robust optimization. The challenge lies in selecting an optimization algorithm that not only performs well, but also adheres to the principles of responsible AI and data governance, particularly concerning the interpretation and application of model outputs. The relevance of derivatives and integrals in understanding the curvature and behavior of the loss function is paramount for effective optimization, but the practical application requires careful consideration of the algorithm's underlying assumptions and its impact on downstream decisions. Correct approach analysis. The correct approach leverages the fundamental understanding of how derivatives inform the direction and magnitude of change in a function, guiding optimization algorithms towards a minimum or maximum. Integrals in this context can be conceptually linked to accumulating error or understanding the overall shape of the loss landscape. By selecting an algorithm that effectively utilizes gradient information derived from derivatives to iteratively adjust model parameters, data scientists can efficiently find optimal solutions. This aligns with best practices in machine learning, where understanding the mathematical underpinnings of algorithms leads to more informed model development and deployment. Furthermore, this approach promotes transparency and interpretability, as the optimization process is grounded in well-understood mathematical principles, facilitating debugging and validation. Incorrect approaches analysis. One incorrect approach involves solely relying on heuristic or black box optimization methods without a foundational understanding of the underlying loss function's behavior. This can lead to suboptimal solutions, slow convergence, or even divergence, as the algorithm may not effectively navigate complex loss landscapes. Ethically, This can be problematic if the resulting model's performance is not thoroughly validated, potentially leading to biased or unfair outcomes that are difficult to diagnose due to the lack of transparency in the optimization process. Another incorrect approach is to choose an optimization algorithm based purely on computational speed, without considering its theoretical guarantees or its suitability for the specific problem's objective function. While efficiency is important, sacrificing accuracy or robustness for speed can result in a model that performs poorly in real-world scenarios, leading to incorrect predictions or decisions. This can have significant ethical implications if these decisions impact individuals or organizations. A third incorrect approach is to ignore the potential for local minima in the loss function and assume that any algorithm will find the global optimum. Derivatives help identify stationary points, but understanding the second derivative, or Hessian, is crucial for distinguishing between minima, maxima, and saddle points. Without this consideration, an optimization process might converge to a suboptimal solution, leading to a model that does not achieve the desired performance, potentially causing financial or operational losses. Professional reasoning. Professionals should approach optimization by first understanding the objective function and its properties. This involves considering the role of derivatives in determining the direction of steepest descent, or ascent, and how integrals might inform the overall error accumulation. When selecting an optimization algorithm, professionals should prioritize methods that are theoretically sound, computationally efficient for the given problem size, and provide a reasonable guarantee of convergence. They should also be aware of the potential for local optima and employ strategies to mitigate this risk, such as using multiple starting points or more advanced optimization techniques. Transparency in the optimization process is key, allowing for validation and debugging, and ultimately ensuring the responsible deployment of AI models. Question 13. Benchmark analysis indicates that initial exploratory data analysis for regional sales performance has generated a standard bar chart comparing average sales figures. While this chart effectively shows the relative performance of each region, it does not reveal the variability or distribution of sales within each region. Provide a more comprehensive understanding of sales patterns and identify potential underlying issues or opportunities. What is the most effective approach for enhancing this visualization? Option A. Replace the bar chart with a pie chart to show the proportion of total sales contributed by each region. Option B. Create a scatter plot to visualize the relationship between average sales and a secondary metric like marketing spend for each region. Option C. Augment the existing bar chart with a box plot for each region to illustrate the distribution, median, and potential outliers of sales data. Option D. Present only the bar chart, as it clearly shows the average sales figures, which are the primary performance indicators. The correct answer is C. Augment the existing bar chart with a box plot for each region to illustrate the distribution, median, and potential outliers of sales data. Explanation. Scenario analysis. This scenario presents a common challenge in data science where the initial presentation of data might be misleading or incomplete, leading to potentially flawed business decisions. The professional challenge lies in identifying the limitations of a standard visualization and proactively addressing them to ensure accurate interpretation and actionable insights. The data scientist must balance the efficiency of readily available tools with the responsibility of providing robust and reliable analysis. Correct approach analysis. The correct approach involves recognizing that a simple bar chart, while effective for comparing discrete categories, may obscure important trends or distributions within those categories. By augmenting the bar chart with a box plot, the data scientist provides a richer understanding of the data. The box plot reveals the median, quartiles, and potential outliers, offering insights into the spread and skewness of the data within each category. This layered visualization approach is best professional practice because it adheres to the principle of transparency and thoroughness in data exploration. It empowers stakeholders with a more comprehensive view, reducing the risk of misinterpretation and enabling more informed strategic decisions. This aligns with ethical data handling principles that prioritize accuracy and completeness in reporting findings. Incorrect approaches analysis. Presenting only the bar chart without further exploration fails to meet the professional obligation to thoroughly investigate data patterns. This approach risks overlooking significant variations within categories, potentially leading to decisions based on incomplete information. From a regulatory perspective, while not a direct violation of specific Azure data science regulations, as these are generally focused on security and privacy, it represents a failure in professional due diligence, which can have indirect ethical and business consequences. Suggesting a pie chart to represent the same data is an inappropriate visualization choice for comparing quantities across multiple categories. Pie charts are best suited for showing proportions of a whole and become difficult to interpret accurately when there are many slices or when the differences between slices are small. Using a pie chart here would hinder effective comparison and obscure the very patterns the analysis aims to uncover, representing a failure in applying best practices for data visualization. Recommending a scatter plot to directly compare the average sales figures across regions would be a misapplication of the visualization type. Scatter plots are ideal for showing the relationship between two numerical variables, not for comparing categorical averages. This choice demonstrates a lack of understanding of appropriate visualization techniques for the given data structure and analytical goal, leading to an ineffective and potentially confusing representation of the insights. Professional reasoning. Professionals should adopt a decision-making process that prioritizes understanding the analytical objective before selecting visualization tools. This involves critically evaluating the initial output of standard visualizations and considering whether they adequately address the underlying questions. A robust approach includes exploring multiple visualization types to uncover different facets of the data. When presenting findings, professionals should aim for clarity, accuracy, and completeness, providing context and acknowledging any limitations of the analysis. This iterative process of exploration, critical evaluation, and thoughtful presentation ensures that data-driven insights are reliable and actionable. Question 14. The audit findings indicate a discrepancy in how a data science team is preparing a large dataset for a predictive model in Azure Machine Learning, specifically regarding the manipulation of feature vectors. The team is debating the most appropriate method to restructure the data for optimal model performance and computational efficiency. One proposed method involves transposing the feature matrix to align features as columns, which is a common step before certain types of model training or when integrating with specific Azure ML services that expect data in a particular orientation. Another suggestion is to perform a matrix multiplication between the feature matrix and a transformation matrix, assuming this will achieve the desired restructuring. A third idea is to apply a matrix inverse to the feature matrix, believing it will normalize the data. Lastly, some suggest simply adding or subtracting a constant matrix to the feature matrix to realign the features. Which of the following approaches best aligns with the principles of effective and appropriate data manipulation for feature engineering in Azure Machine Learning, considering the nature of vector and matrix operations? Option A. Adding or subtracting a constant matrix to the feature matrix without a specific analytical justification for restructuring. Option B. Forming a matrix multiplication between the feature matrix and an arbitrary transformation matrix to restructure the data. Option C. Transposing the feature matrix to change the orientation of features, which is a standard technique for preparing data for various machine learning algorithms and services within Azure ML. Option D. Applying a matrix inverse to the feature matrix to normalize the data. Correct answer is C. Transposing the feature matrix to change the orientation of features, which is a standard technique for preparing data for various machine learning algorithms and services within Azure ML. Explanation. The audit findings indicate a potential misinterpretation of how vector and matrix operations are applied in the context of Azure Machine Learning data processing, specifically concerning data transformation and feature engineering. This scenario is professionally challenging because data scientists must ensure that their mathematical operations on data are not only computationally correct, but also align with the intended analytical goals and do not introduce unintended biases or data integrity issues. The regulatory framework for this exam, which implicitly governs the responsible use of Azure services, emphasizes accuracy, security, and ethical data handling. The correct approach represents best professional practice because it demonstrates a nuanced understanding of matrix transpose and its application in preparing data for downstream machine learning models. A matrix transpose is fundamental for reshaping data. For instance, when transitioning from a row-oriented feature representation to a column-oriented one, or vice versa, which is often a prerequisite for specific algorithms or for efficient computation in distributed systems like Azure. This operation preserves the integrity of the data's relationships while making it compatible with various analytical tools and models available within Azure ML. Adhering to this understanding ensures that data transformations are purposeful, reproducible, and contribute to the reliability of the machine learning pipeline, aligning with the implicit regulatory expectation of robust and trustworthy AI systems. An incorrect approach that focuses solely on matrix multiplication without considering the dimensionality or the specific transformation needed for feature engineering is professionally unacceptable. Matrix multiplication has strict rules regarding compatible dimensions, and applying it without understanding the data's structure or the desired outcome can lead to errors that corrupt the dataset or render it unusable for modeling. This failure to adhere to the mathematical prerequisites of matrix multiplication, when applied to data, can result in a loss of data integrity and inaccurate model training, violating the implicit regulatory expectation of data accuracy and reliability. Another incorrect approach that suggests using matrix inverse for simple data reshaping or feature scaling is also professionally unacceptable. The matrix inverse is a complex operation typically used in solving systems of linear equations or in specific statistical methods. Applying it to general data transformation tasks is computationally inefficient, often unnecessary, and can introduce numerical instability if the matrix is not well conditioned. This demonstrates a lack of understanding of the appropriate tool for the job, potentially leading to performance issues and unreliable results, which contravenes the implicit regulatory expectation of efficient and sound data processing practices. Finally, an incorrect approach that advocates for arbitrary matrix addition or subtraction without a clear analytical purpose or compatible dimensions is professionally unacceptable. While these operations are mathematically defined, their application in data science must be driven by a specific analytical goal, such as combining datasets with identical feature sets or applying a consistent offset. Performing these operations without justification or proper dimension matching can lead to nonsensical data transformations, data corruption, and ultimately, flawed model performance, failing to meet the implicit regulatory expectation of purposeful and accurate data manipulation. The professional reasoning process for such situations involves 1. Clearly defining the data transformation objective. 2. Understanding the mathematical properties and constraints of vector and matrix operations. 3. Selecting the operation that precisely achieves the objective while respecting data integrity and computational efficiency. 4. Validating the transformation's impact on the data and its suitability for subsequent modeling steps. This systematic approach ensures that data science practices are both technically sound and ethically responsible within the Azure ecosystem. Question 15. Investigation of a large customer dataset for a new recommendation engine reveals several data quality issues during the initial profiling phase, including a significant percentage of missing values in key demographic fields and inconsistent formatting in address fields. The data science team is under pressure to deliver a prototype quickly. Which of the following approaches best balances the need for speed with the imperative of data integrity and responsible AI development? Option A. Conduct a thorough analysis of the missing data patterns and the nature of the inconsistencies. Develop targeted imputation strategies for missing values and implement standardized formatting rules for addresses, followed by reprofiling to confirm improvements before proceeding with model training. Option B. Manually impute all missing demographic values with a single common value, e.g., unknown, and apply a generic address cleaning script without understanding the specific types of inconsistencies present. Option C. Discard the entire customer dataset due to the identified quality issues, as it is too risky to build a recommendation engine on unreliable data, and request a new, cleaner dataset. Option D. Proceed immediately with training the recommendation engine using the raw data, assuming that the model will be robust enough to handle the imperfections, and that the missing values will not significantly impact performance. The correct answer is A. Conduct a thorough analysis of the missing data patterns and the nature of the inconsistencies. Develop targeted imputation strategies for missing values and implement standardized formatting rules for addresses, followed by reprofiling to confirm improvements before proceeding with model training. Explanation. This scenario presents a common challenge in data science, ensuring the integrity and suitability of data before building models. The professional challenge lies in balancing the need for timely insights with the imperative to maintain data quality and adhere to responsible AI principles, which are increasingly codified in regulatory frameworks. Careful judgment is required to identify and address data quality issues without introducing bias or compromising the data's representativeness. The correct approach represents best professional practice because it directly addresses the identified data quality issues through systematic profiling and targeted remediation. This aligns with the principles of responsible data handling and AI development, emphasizing transparency and accuracy. By understanding data characteristics and identifying anomalies, the data scientist can ensure that the subsequent model training is based on reliable data, minimizing the risk of generating biased or inaccurate predictions. This proactive stance is crucial for building trust in AI systems and complying with emerging regulations that mandate data quality and fairness. An incorrect approach that involves immediately proceeding with model training without addressing the identified data quality issues is professionally unacceptable. This failure constitutes a significant ethical lapse and a potential regulatory violation. It risks propagating errors and biases present in the raw data into the model, leading to unfair or discriminatory outcomes. Such an approach demonstrates a disregard for data integrity and the potential downstream impact of flawed data, which can have serious consequences for individuals and organizations. Another incorrect approach, which is to discard the entire dataset due to minor quality issues without further investigation, is also professionally unsound. While data quality is important, wholesale discarding of data can lead to loss of valuable information and may not be the most efficient or effective solution. It can also be seen as an abdication of responsibility to find workable solutions. This approach fails to explore more nuanced remediation strategies and may not be justifiable if the quality issues are addressable. A third incorrect approach, which is to manually impute missing values without understanding the patterns of missingness or the nature of the data, is problematic. While imputation is a common technique, performing it without proper profiling and understanding can introduce artificial patterns or biases into the dataset. This can lead to misleading model performance and inaccurate conclusions. It lacks the systematic rigor required for responsible data handling. The professional decision-making process for similar situations should involve a structured approach to data profiling. This includes understanding the data's schema, distributions, and relationships. Identifying anomalies, missing values, and inconsistencies is a critical first step. Based on this profiling, a strategy for data cleaning and remediation should be developed, considering the impact of each step on the data's integrity and representativeness. This process should be documented thoroughly, and any assumptions made during cleaning should be clearly stated. The goal is to create a robust and reliable dataset that accurately reflects the underlying phenomena, thereby enabling the development of trustworthy and effective AI solutions. Question 16. What factors determine the optimal number of principal components to retain when applying principal component analysis, PCA, for dimensionality reduction in an Azure machine learning solution? Option A. The arbitrary selection of a fixed number of components that is commonly used in similar industry applications. Option B. The order in which principal components are generated by the PCA algorithm, irrespective of their associated variance. Option C. The subjective ease of interpreting the meaning of the principal components, even if they explain minimal variance. Option D. The cumulative proportion of variance explained by the selected components and the observed elbow point in a scree plot. Correct answer is D. The cumulative proportion of variance explained by the selected components and the observed elbow point in a scree plot. Explanation. Scenario analysis. This scenario presents a common challenge in applied data science, where a data scientist must select the most appropriate dimensionality reduction technique for a given business problem. The challenge lies in balancing the need for computational efficiency and interpretability with the potential loss of information. Misjudging this balance can lead to models that are either too complex and slow to deploy, or too simplistic and fail to capture crucial patterns, impacting business decisions and potentially leading to financial losses or missed opportunities. The Azure Data Scientist Associate certification emphasizes practical application, making the choice of technique a critical decision point. Correct approach analysis. The correct approach involves evaluating the inherent variance in the dataset and the desired level of information retention. Eigenvalues, in the context of PCA, represent the amount of variance explained by each corresponding eigenvector, principal component. A data scientist should prioritize components with larger eigenvalues, as they capture more of the original data's variability. The decision to retain a certain number of components is often guided by a cumulative variance threshold e.g., retaining components that explain 95% of the variance, or by observing an elbow in a scree plot, indicating diminishing returns in information gain. This approach is best professional practice because it is data-driven and directly addresses the core purpose of PCA: to reduce dimensions while preserving as much of the original data's information as possible, leading to more efficient and potentially more robust models. This aligns with the principles of responsible AI and efficient resource utilization within Azure. Incorrect approaches analysis. One incorrect approach is to arbitrarily select a fixed number of principal components without considering the variance explained. This fails to account for the specific characteristics of the dataset. If too few components are chosen, significant information is lost, leading to a model that may not accurately represent the underlying patterns. If too many are chosen, the dimensionality reduction is insufficient, negating the benefits of PCA and potentially leading to overfitting. This approach lacks analytical rigor and can be seen as a failure in due diligence, potentially leading to suboptimal business outcomes. Another incorrect approach is to prioritize components solely based on their order of appearance without regard to their associated eigenvalues. Eigenvectors are ordered by the magnitude of their eigenvalues, with the first eigenvector corresponding to the largest eigenvalue. Ignoring this ordering means that the most important sources of variance might be discarded, leading to a severe loss of information. This is a fundamental misunderstanding of how PCA works and represents a significant professional failing in applying the technique correctly. A third incorrect approach is to select components based on subjective interpretability alone, even if they explain very little variance. While interpretability is important, it should not come at the expense of capturing meaningful data patterns. If the components that are easiest to interpret explain negligible variance, they are unlikely to contribute to a predictive model's performance. This approach prioritizes a secondary goal over the primary objective of dimensionality reduction for improved model performance, leading to a potentially misleading or ineffective model. Professional reasoning. Professionals should adopt a decision-making framework that begins with understanding the business objective and the characteristics of the data. For dimensionality reduction using PCA, this involves 1. Performing PCA on the dataset. 2. Analyzing the eigenvalues to understand the variance captured by each principal component. 3. Visualizing the cumulative explained variance, e.g., using a scree plot to identify a suitable number of components that balance information retention with dimensionality reduction. 4. Considering the trade-off between information loss and model complexity/performance. 5. Validating the chosen component's impact on downstream model performance. This systematic approach ensures that the chosen dimensionality reduction strategy is aligned with both technical requirements and business goals, adhering to best practices for data science within the Azure ecosystem. Question 17. When evaluating how a matrix represents a linear transformation within an Azure ML pipeline and needing to explain its impact to a business stakeholder, which approach best demonstrates a professional understanding of the concept's practical implications? Option A. Stating that Azure ML's built-in functions abstract away the complexities of linear transformations, making it unnecessary to understand the underlying matrix representation for practical application. Option B. Focusing on the theoretical definition of a linear transformation and its axiomatic properties, without directly connecting it to the specific matrix or its effect on the dataset. Option C. Detailing the specific mathematical operations involved in matrix multiplication and how each element of the matrix contributes to the transformation's algebraic properties, such as its rank or nullity. Option D. Describing how the matrix reshapes the data's feature space, potentially altering relationships between variables or reducing dimensionality, and explaining this effect in terms of how it might simplify or focus the data for a downstream model. The correct answer is D. Describing how the matrix reshapes the data's feature space, potentially altering relationships between variables or reducing dimensionality, and explaining this effect in terms of how it might simplify or focus the data for a downstream model. Explanation. This scenario is professionally challenging because it requires a data scientist to translate abstract mathematical concepts into practical, interpretable insights for stakeholders who may not have a deep mathematical background. The core challenge lies in bridging the gap between the underlying mechanics of linear transformations represented by matrices and their real-world implications in an Azure ML context. The correct approach represents best professional practice because it focuses on understanding the asterisk effect asterisk of the matrix as a linear transformation on the data, rather than getting lost in the matrix multiplication itself. This aligns with the Azure Data Scientist Associate's responsibility to not only build models, but also to communicate their behavior and impact effectively. By focusing on how the transformation alters data distribution, dimensionality, or feature relationships, the data scientist can provide actionable insights. This approach is ethically sound as it promotes transparency and understanding, preventing misinterpretation of model behavior. It adheres to the principles of responsible AI by ensuring that the application of linear transformations is understood in terms of its impact on data and potential outcomes, which is crucial for compliance with data governance and fairness guidelines that might be implicitly expected within a regulated environment, even if specific Azure regulations aren't explicitly detailed for this exam. An incorrect approach that focuses solely on the mathematical properties of the matrix e.g., its determinant or eigenvalues, without relating them to the data transformation, fails to provide practical value. This is professionally deficient because it prioritizes theoretical completeness over practical application, hindering stakeholder comprehension and decision-making. Ethically, it risks creating a black box, where the model's behavior is understood mathematically, but not contextually, potentially leading to unintended consequences or biased outcomes if the transformation's impact on sensitive attributes is not considered. Another incorrect approach that attempts to explain the transformation using complex mathematical jargon without simplification or analogy is also professionally unacceptable. This fails to meet the communication requirements of a data scientist, leading to confusion and distrust from stakeholders. It can be seen as an ethical failure to adequately inform and educate those who rely on the data scientist's expertise. A further incorrect approach that dismisses the importance of understanding linear transformations altogether, assuming that Azure ML tools handle it implicitly, is professionally negligent. This overlooks a fundamental aspect of data manipulation and feature engineering, potentially leading to suboptimal model performance or the introduction of unforeseen biases. It fails to uphold the professional standard of understanding the tools and techniques being employed. The professional reasoning framework for such situations involves 1. Understanding the stakeholder's needs and technical background. 2. Identifying the core concept to be explained, linear transformation via matrices. 3. Translating the mathematical concept into its functional impact on the data, e.g., rotation, scaling, projection, dimensionality reduction. 4. Using analogies and visualizations where appropriate to simplify complex ideas. 5. Focusing on the what and why of the transformation's effect, not just the how of the matrix operations. 6. Considering the implications of the transformation on data fairness, interpretability, and downstream model performance. Question 18. The performance metrics show a significant drop in model accuracy when deployed in a production environment compared to offline testing, particularly for a customer churn prediction model. Upon investigation, it's discovered that a substantial portion of the customer lifetime value feature has missing values, and there are several extreme, unusually high values in the support ticket resolution time feature. The business stakeholders are eager to deploy a fix quickly to improve the live model's performance. What is the most responsible and effective approach to address these data quality issues? Option A. Replace all missing customer lifetime value with 0, assuming that customers with no recorded lifetime value are not valuable, and remove all support ticket resolution time outliers entirely from the dataset. Option B. Remove all records with missing customer lifetime value and all records with support ticket resolution time exceeding the median, as these are likely data entry errors. Option C. Impute all missing customer lifetime value with the overall mean and cap all support ticket resolution time values at the 95th percentile to reduce their influence. Option D. Conduct a thorough analysis to understand the patterns of missingness in customer lifetime value and investigate the root cause of extreme support ticket resolution time values. Then apply imputation or treatment methods that are contextually appropriate and minimally distorting. The correct answer is C. Impute all missing customer lifetime value with the overall mean and cap all support ticket resolution time values at the 95th percentile to reduce their influence. Explanation. This scenario presents a professional challenge because the data scientist must balance the need for model performance with the ethical implications of data manipulation. The Azure Data Scientist Associate certification implies adherence to Microsoft's responsible AI principles and general data science best practices, which prioritize transparency, fairness, and accuracy. The challenge lies in deciding how to handle missing values and outliers in a way that is both technically sound and ethically defensible, especially when the business objective might implicitly favor a certain outcome. The correct approach represents best professional practice because it prioritizes understanding the root cause of missing data and outliers before applying imputation or treatment methods. This involves domain expertise and a thorough investigation into why data is missing or anomalous. For missing values, techniques like identifying patterns of missingness e.g., missing completely at random, missing not at random, and choosing imputation methods e.g., mean, median, mode, regression imputation, or more advanced methods that align with the data's characteristics and the problem's context are crucial. For outliers, understanding if they represent genuine extreme values or data errors is paramount. If they are errors, they should be corrected or removed. If they are genuine, their impact on the model should be assessed, and appropriate treatment e.g., winsorizing, transformation, or using robust models should be applied. This meticulous, data-driven, and context-aware approach ensures that the resulting model is reliable, fair, and interpretable, aligning with responsible AI principles by avoiding the introduction of bias or misleading insights through arbitrary data manipulation. An incorrect approach that involves arbitrarily imputing all missing values with the mean without investigating the nature of the missingness is professionally unacceptable. This can introduce bias if the missing data is not missing completely at random, distorting the true distribution of the data and leading to inaccurate model predictions. Ethically, this is a failure of due diligence and transparency. Another incorrect approach, such as removing all rows with any missing values or outliers without a clear justification or impact assessment, is also professionally problematic. This can lead to significant data loss, potentially removing valuable information, and creating a biased dataset if the missingness or outliers are not uniformly distributed. This violates the principle of maximizing the utility of available data and can lead to a model that is not representative of the real-world phenomenon. A third incorrect approach, such as aggressively transforming or capping all outliers to fit a specific distribution without understanding their origin, can mask important signals or create artificial patterns. This can lead to a model that performs poorly on unseen data or makes unfair predictions, violating principles of accuracy and fairness. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the data and the business problem thoroughly. 2. Investigate the nature and extent of missing values and outliers. 3. Formulate hypotheses about the causes of missingness and outliers. 4. Select appropriate data cleaning and imputation techniques based on the investigation, domain knowledge, and the specific requirements of the model. 5. Document all data cleaning steps and their justifications. 6. Evaluate the impact of cleaning techniques on data distribution and model performance. 7. Consider the ethical implications of each decision, particularly regarding fairness and bias. 8. Communicate findings and decisions transparently. Question 19. System analysis indicates that a team of data scientists requires access to a large dataset stored in Azure Blob storage for the purpose of training machine learning models. The data is considered sensitive and is subject to organizational data governance policies that mandate strict access controls and auditability. The data scientists only need to read the data and should not have the ability to modify or delete it. Which of the following methods best aligns with these requirements for accessing the data? Option A. Generate shared access signature (SAS) tokens with write and delete permissions for the storage container and provide these tokens to the data scientists. Option B. Utilize Azure CLI commands with appropriate Azure role-based access control (RBAC) roles assigned to the data scientists, granting them read-only permissions to the specific storage container. Option C. Distribute Azure Storage account keys directly to each data scientist, allowing them full administrative access to the storage account. Option D. Grant all data scientists the contributor role at the storage account level. The correct answer is B. Utilize Azure CLI commands with appropriate Azure Role-Based Access Control (RBAC) roles assigned to the data scientists, granting them read-only permissions to the specific storage container. Explanation. Scenario analysis. This scenario presents a common challenge for data scientists, securely and efficiently accessing sensitive data stored in Azure Blob Storage for model training. The professional challenge lies in balancing the need for timely data access with stringent security and compliance requirements inherent in handling potentially regulated data. Incorrect choices can lead to data breaches, compliance violations, and operational inefficiencies. Careful judgment is required to select the method that aligns with both technical needs and organizational policies. Correct approach analysis. Using Azure CLI commands with appropriate role-based access control (RBAC) assignments is the best professional practice in this scenario. The Azure CLI provides a programmatic and scriptable way to interact with Azure resources, including blob storage. When combined with RBAC, it allows for granular control over who can access what data and perform which operations. This approach ensures that access is granted based on the principle of least privilege, a fundamental security and compliance tenet. By leveraging RBAC, the organization can audit access, revoke permissions easily, and maintain a clear record of data access, all of which are critical for regulatory compliance and data governance. This method is robust, auditable, and scalable for managing data access across multiple projects and users. Incorrect approach is analysis. Granting broad contributor-level access to the storage account for all data scientists is a significant regulatory and ethical failure. Contributor access grants extensive permission, including the ability to delete or modify data, which far exceeds the read-only requirement for model training. This violates the principle of least privilege, increasing the risk of accidental data loss or malicious alteration. It also makes auditing data access extremely difficult, as it's impossible to distinguish between legitimate training data access and unauthorized modifications. Such an approach would likely contravene data protection regulations that mandate strict access controls and data integrity. Using Azure Storage Explorer with Shared Access Signature (SAS) tokens that have write or delete permissions is also professionally unacceptable. SAS tokens can be useful for temporary, scoped access. Granting write or delete permissions to data scientists for read-only model training purposes introduces unnecessary risk. This bypasses the more robust RBAC model and can lead to unauthorized data modifications or deletions, compromising data integrity and potentially violating compliance mandates. Furthermore, managing and revoking numerous SAS tokens can become cumbersome and error-prone, increasing the likelihood of lingering excessive permissions. Providing direct access credentials, e.g., account keys, to the storage account to all data scientists is a severe security and compliance failure. Account keys grant full administrative access to the storage account, including read, write, delete, and management operations. Sharing these keys broadly is akin to giving away the master key to the entire data repository. This practice is highly insecure, makes auditing impossible, and directly violates data protection principles and regulatory requirements for secure data handling. It creates an unacceptable risk of data breaches and unauthorized access. Professional reasoning. Professionals should adopt a decision-making framework that prioritizes security, compliance, and operational efficiency. This involves 1. Understanding the data's sensitivity and any applicable regulatory requirements. 2. Identifying the minimum necessary permissions for each user or role to perform their tasks. 3. Selecting access methods that support granular control and auditability, such as RBAC. 4. Implementing access controls programmatically or through secure management interfaces, avoiding direct credential sharing or overly permissive access. 5. Regularly reviewing and auditing access permissions to ensure ongoing compliance and security. In this case, the need for read-only access for model training strongly points towards RBAC with read permissions, managed via Azure CLI for automation and control. Question 20. Research into optimizing an existing Azure Data Factory pipeline for improved processing speed and reduced operational costs. A data scientist is considering several approaches. The pipeline ingests data from multiple sources, performs transformations, and loads it into Azure Synapse Analytics. The primary goal is to enhance efficiency without compromising data accuracy or introducing new security vulnerabilities. Which of the following strategies best aligns with best practices for process optimization in this context? Option A. Consolidate multiple transformation steps into single, complex activities to reduce the overall number of pipeline components, even if it obscures individual step logic. Option B. Immediately scale up all compute resources associated with the pipeline activities to their maximum capacity to ensure the fastest possible processing. Option C. Gradually introduce optimizations, starting with parameter tuning and incremental data processing, while continuously monitoring performance and data integrity. Option D. Undertake a complete rewrite of the pipeline logic to incorporate the latest Azure features, assuming this will inherently improve efficiency. The correct answer is C. Gradually introduce optimizations, starting with parameter tuning and incremental data processing, while continuously monitoring performance and data integrity. Explanation: scenario analysis. This scenario presents a common challenge in data science, optimizing data pipelines for efficiency and cost-effectiveness while ensuring data integrity and compliance. The professional challenge lies in balancing performance gains with potential risks, such as introducing errors, violating data governance policies, or incurring unexpected costs. Careful judgment is required to select an optimization strategy that aligns with business objectives and regulatory requirements. Correct approach analysis. The correct approach involves a phased implementation of optimization, starting with less intrusive methods like parameter tuning and incremental data processing. This represents best professional practice because it allows for continuous monitoring and validation at each stage, minimizing the risk of widespread disruption or data corruption. Azure Data Factory's orchestration capabilities facilitate this by enabling granular control over pipeline execution, logging, and error handling. This methodical approach ensures that any performance improvements are validated and that data quality is maintained, adhering to principles of responsible AI and data management, which are implicitly expected within the Azure ecosystem's governance frameworks. Incorrect approaches analysis. Implementing a complete rewrite of the data pipeline without thorough testing and validation is a significant regulatory and ethical failure. This approach risks introducing subtle bugs that could lead to data inaccuracies, impacting downstream analytics and decision-making. Such a failure could violate data integrity principles and potentially lead to non-compliance with data governance policies if data quality is compromised. Aggressively scaling up compute resources without a clear understanding of the bottlenecks or the impact on data processing logic is also professionally unsound. This can lead to unnecessary expenditure and may not address the root cause of inefficiency, potentially masking underlying pipeline design flaws. From a compliance perspective, uncontrolled resource scaling could also lead to overspending, which might be scrutinized under financial governance policies. Focusing solely on reducing the number of pipeline steps without considering the impact on data transformation logic or error handling mechanisms is another flawed strategy. This can lead to oversimplified pipelines that miss critical data validation or cleansing steps, compromising data quality, and potentially leading to the generation of misleading insights. This directly contravenes the ethical obligation to ensure the accuracy and reliability of data used for decision-making. Professional reasoning. Professionals should adopt a data-driven and iterative approach to pipeline optimization. This involves 1. Profiling and monitoring the existing pipeline to identify specific bottlenecks and areas for improvement. 2. Prioritizing optimizations based on potential impact, complexity, and risk. 3. Implementing changes incrementally with robust testing and validation at each step. 4. Leveraging Azure Data Factory's features for monitoring, logging, and alerting to track performance and identify issues. 5. Documenting all changes and their impact on pipeline performance and data quality. 6. Regularly reviewing and refining the pipeline based on ongoing performance metrics and evolving business requirements.